Hello class, so this is going to be the first video lecture for CSE 5250 section 2. This is the online asynchronous section in contrast to section 1, which is an in-person section of CSE 5250. For those who were initially enrolled in section 1 and are now joining section 2, welcome back. This is CSE 5250 section 2. I'm your instructor, Giovanni Orijuela, and this is parallel programming. This will be the presentation. This is going to be the video lecture for week 1, where I basically go through the syllabus, a little bit about myself, and what we'll be doing for our first assignment. So with that, welcome to parallel programming, and let's begin with how I got to where I am right now. So, this image doesn't really have the same weight as it did when I showed it in my in-person section of 5250. Basically, the answer to how I got here can be taken to be literal. And in that interpretation, the answer to how I got here is basically just driving down the 215 and then taking the exit for University Parkway, parking in the charging station because I have an electric car and I have the ability to charge my car on campus because I have an app on my phone that lets me use the charging stations there. Walking to what I thought was the physical science building, but was in fact the biology building. And then backtracking to what's actually the physical science building, and then finding my way to the classroom that was assigned. So that's the literal answer to how I got here. Even though I'm back at home right now, that's basically the answer that I initially posed for how I got here. But it's really the satisfactory answer if you think about it. How I got here is really a journey not through space, but really through time as well. So how I got here, how did I get here? Where do we start? Well, we get to start with my earliest ancestors, but then there's Pangea before that, so let's start around 2016. So 2016 was when I first transferred to CSUSB as a computer science major because I knew from a very young age that I wanted to do something with computers as a career. So, 2016 2016 was when I first transferred to CSUSB from... Before that, I was taking classes at a community college in a place known as the Morongo Basin. That's just a general geographic area. If you know where the Morongo Basin is, I can tell you right now that it's two things. One, it's far. Maybe not as far as other places, but it's pretty far enough that it takes about a 2-hour drive to get from San Bernardino to the Morongo Basin. And two, it's hot. It's near the border between two different deserts, the Mojave and Sonoran deserts. But really, the border between those two deserts really converge around the national park area, Joshua Tree National Park, by the way. So yeah, all you need to know is that where I came from was pretty far, or rather, far enough away that driving becomes a bit of a chore. Anyway, that's how I started off at CSUSB. It was around 2017 or 2018 that I decided to myself, what if I wanted to do something with all the oddball skills that I've accumulated for myself that isn't necessarily related to computer science. So, stuff such as 2D illustration, 3D modeling, because at the same time I was looking at computer science, I was also looking at game development as well as a possible as a way of using all my oddball skills that I said I'd been accumulating for myself. So I said to myself, what if I dual majored in computer science and game development? And so that was what I did for the next few years after that. It was around 2020 that I finally graduated computer science and game development with a bachelor's degree in both. But not quite at the same time, but close enough that I can say that I graduated in 2020 for both. It was around that time that I said to myself, again, what if I don't get a job in game dev? What if I don't get a job in game dev right away? What if I instead wanted to go further in computer science? What if I wanted to get my master's degree in computer science? Because, to have a master's degree in computer science is basically one way to get around in the volatile market. I guess I wouldn't say volatile, but in demand market for people who are specialized in computer science. But it's basically the reasoning for me wanting to go for game development initially was to put to use all my non-CS skills, and going for my master's degree would better ensure that I getting a master's degree basically better ensures that I get a well-paying job in some field that requires people who specialize in computer science. So it's basically a sort of redundancy, just in case the game dev path doesn't exactly work out. And this was all in 2020, so you would think that I came back to CSUSB because of the pandemic. But really, what happened was the reverse. I made the decision to go back to grad school before COVID hit. So I guess it's a good thing that I did. I guess it's a good thing that I made that decision in advance, because there's this idea that you would pick up new skills during the pandemic so that you would come out of it better emboldened or better off than you came in to the pandemic initially. It's hard to say that we are truly out of the pandemic right now. It's still ongoing, as you can see, but at least I can say that there is a light at the end of the tunnel. Alright, moving on. As I said, I graduated with both my Bachelor's of Science in Computer Science and Bachelor of Arts in Game Development around the same time, in 2020. I am currently going for my master's degree in computer science, and that is currently in progress. And that's me right there. Face mask and all, to signify that 2020 was a exceptionally weird time for those who were graduating. Now, the next slide is basically the words go over the syllabus. So, with that, let's just quickly go over the syllabus. As I said, this is section 2 of CSE-5250. This is the online asynchronous section. As I said, I'm the instructor, Giovanni Orijuela. Email is the best way to contact me. This is in the syllabus, and the syllabus is also on Canvas, but I also have my email address on Canvas as well. So this is my email address. As I said, this is an online asynchronous course. There's a prereq of CSE 4010, or if you were, or if you took it under the quarter system, it was CSE 401. This is CSE 5250 and was known as CSE 5250 under the quarter system. Sometime between then and when I graduated was the decision to go from being a quarter system to a semester system. And of course, that transition was basically in the middle of COVID. So you can imagine how hectic it was on the administrative side just to transition from one thing to another, only to have a worldwide pandemic befall on you. Right, so grading. So much of the course will be basically looking at getting a program to be parallel, starting from a program that was initially written to be sequential. So 40% of the grade will be basically various programming projects using different ways of making a parallel program. The midterm is 20% of your grade, and I'll get more into the midterm later, but I will say it is not a exam, but rather a sort of project, if you will. Final is 30% of your grade. That's not going to be an exam either, but I will say it's to be determined right now. Participation in quizzes. So this is an online asynchronous course, so I can't really give out quizzes. But I will give out short answer questions. Sometimes I will give out short answer questions, and the intent is you have to answer it with some sort of answer, and the answer to that question, there may be more than one possible answer to the question. And you will have ample time to answer these questions. They're basically due a week after they are posted. And these questions are, and these other assignments are basically 10% of your grade. Here's the grading scale. Again, this syllabus is online on Canvas. So here we have our tentative schedule for what we'll be doing for the next 15 weeks. Week 1 is basically going over the syllabus and looking at the Sieve of Eratosthenes as a benchmark program. After that, we're going to look at 3 different ways of making a parallel program. One of them is using OpenMP, the other one is using NVIDIA CUDA, and the third one is using MPI. And over the course, and over these, over this span of time, we'll also be doing benchmarks to see what kind of speed up we can get out of each means of making a parallel program. After that, we'll be looking at other applications of parallel programming, because the last time I taught this course, it was basically focused on getting the Sieve to work. But of course, there's more applications there's more uses for parallel programming. So basically the question is, what else can we do? Well, the answer is quite a lot. We'll talk more about that in a second, but one interesting use case that I came across was the idea of brute force. Brute forcing a seed for a random number generator. I can only assume that a lot of you have already heard of what Minecraft is. And if you've been looking at Minecraft recently, you may have heard of these efforts of people finding Minecraft seeds when all they had to go off was just an image, a screenshot, if you will, of Minecraft. So basically, if all you have is a screenshot of Minecraft, the idea is you can find out what the seed was. So if you type in the seed, you'll get the same terrain as shown as in the picture. If you have the time, try to look up if you have the time, try to look up this in YouTube. Minecraft pack.png seed. It's basically a story. It's basically explaining how the seed for what is believed to be the most viewed image in all of Minecraft. It's basically how did they find the seed for this image here? It's shown here. Rather, it's actually this image here. See? But again, sorry about that. We'll talk about more about brute force when we get to that point. Now, as I said, this is an online asynchronous course. Will we have Zoom meetings? Well, that depends on... Well, we might have Zoom meetings depending on whether a lot of people need help. So, we may have Zoom meetings upon request. But there will at least be one video lecture posted each Wednesday. Academic policies. The student is referred to academic regulations and procedures in the CSUSB Bulletin of Courses for the university's policies on course withdrawal, cheating, and plagiarism. Academic honesty. In short, don't cheat, and don't plagiarize either. At best you'll get a grade of a 0, and at worst you may face expulsion. You are allowed to collaborate with one another if you need help on anything, but just be sure whatever work you have is individual work. Adding and dropping a class. The CSUSB policies for dropping and adding classes can be found at this link here. Students are expected to take notice. And if you're in need of an accommodation for a disability in order to participate in the class, please contact Services to Students with Disabilities at this number here. It's the student's responsibility to seek academic accommodations for a verified disability in a timely manner. So that's basically it for the syllabus. Now, I'll be going a bit more in detail about the Sieve of Eratosthenes with section 1. In fact, it's a Tuesday night. It's a little late right now, and I'm recording this video in advance for section 2. So, before we get into the Sieve of Eratosthenes, can you think of a program that you use that is parallelized? That is there a program that you regularly use that is parallelized? Pause the video and think about that, and then I'll talk about a few examples that I can think of. Alright, so are there programs that you regularly use that is parallelized? Well, yeah, there are many programs that are, well, parallelized, or at least multi-threaded. And what do I mean by that? Well, this is a concept that comes from operating systems. The idea of a multi-threaded program is that you can offload certain tasks to each thread, so that even if there's a lot of work to be done, at least there's one thread free to do something else. Or rather, if one thread is overburdened with a lot of work, at least some part of the program is still responsive. So basically, if you have a text editor, or better yet, a word processor, like this, you would have several threads doing different things. One thread is basically listening to input from the user. Another thread would be, for example, rendering images, because sometimes you'll have to insert an image into Microsoft Word, and if it's a single-threaded program, you're basically just sitting there waiting for the image to render. And that time waiting is basically time that you could be using to type more of whatever it is that you're working on. So one thread could just be delegated the task of rendering the image while you can just continue on typing. Since I'm signed into a Microsoft account, there could also be one thread sending and receiving packets from a server. And that's basically the basis of that's basically one example of multi-threading. Another example of multi-threading would be in a video game. In fact, a video game would have more things to a video game is pretty intensive in terms of what things to calculate. I'll explain. So from the previous example, you would have one thread listening to user input. Another thread could be handling the sound engine. Another thread could be handling the physics engine, because this could be a video game that has physics. So if you chop down a tree and it falls on you, for example, the tree could basically fall onto you and then roll down a hill. And that requires some physics calculations. All the while, you would have to have a sound engine playing the appropriate sound effects for the tree falling on you, you making an appropriate sound for having a tree fall on you, and the video game would also have to play sounds for the tree hitting the ground and rolling away. There would also have to be a game loop. There would also be a game loop where it would have to calculate how much damage was done to you when the tree fell on you. If this is an online game, they would have to send that information to a server and then receive that information back. And of course, rendering. Because this is a video game, you have to somehow render each frame of the tree falling on you. Or rather, the task is called Rasterization. So how does a computer draw an image like that in a video game? Well, one way is to just have the task be delegated to the CPU. But these days, oftentimes with video games that have high graphics requirements, the task of rendering each frame is done by the GPU instead of the CPU. So how is it that the GPU is being delegated this task of rendering a frame? Well, it's actually pretty complicated in that, well, there's just a lot of pixels to calculate. For a 19 by 20 by 1080 image, you have about 2 million pixels. Since I'm working with a 4K monitor, I'm dealing with 4 times as many pixels. That's 3,840 times 2,160, and that's about 8 million. So if I play, for example, any one of the games I have in my Steam library, for example, my graphics card is going to be given the task of calculating 8 million pixels worth of visual data many times a second. How many times a second will depend on what's known as the frame rate, but ideally, this would be 30 or 60 frames per second. So, 8 million pixels, 30 times a second, or 60 times a second. or based on how, it's a little more nuanced because in video games you have frame rates that can fluctuate based on the how intensive it is to calculate the to even render the image itself. But now that I bring up rendering, let's look at another application, another program, if you will, where parallel programming is of great benefit to make sure that the program can actually calculate anything in a reasonable amount of time. So, I have here a image of various vehicles here. And within this dotted line, this red square here, I'm going to render a 4096 by 4096 image that is shown within this red square here. So what I can also do is I can move around a little bit. Basically I want to try to get a pretty good picture for the sake of example. Now I'm using a rendering engine that's known as Eevee, like the Pokemon. But I think that might be a coincidence. I haven't checked. There was an older rendering engine called Cycles. I tried to render this using the Cycles engine, but I tried to render this using the Cycles engine earlier, and it didn't really render properly. But if I tried to render it anyway, this is a 4096 by 4096 image, and you might see the outline of a bunch of squares snaking around the entire image in a sort of fractal curve. The specifics are a bit beyond the scope of this lecture because it's pretty math heavy, but the point is each square in this snaking line of each square in this image represents a section, a tile as it's called, being rendered by one of the 16 threads that my CPU has, because I have a 16-thread CPU. And it's only in recent times that these kinds of CPUs have become more widely available because they've just gotten cheaper over the years. In fact, I built my current computer around 2017, which is when the Ryzen line of CPUs just came out, and they turned out to be pretty good for the value. But that's just speaking from my own experience with AMD CPUs. The reason I got into AMD CPUs in the first place was because I had no idea what Intel was trying to sell me. So, the rendering is done, and as I said, it didn't really work, but let's try to compare it if I tried to switch over from CPU rendering to Eevee. The previous rendering engine was called Cycles, and it's around Blender version 2.9 something or other. This was a while ago, and I actually haven't updated Blender in a while. If I tried to render the same image using the Eevee rendering engine, watch how fast it renders. That fast. Not even 2 seconds. And if we go back to Task Manager, you can see the little spike in activity that was from the GPU being given information from Blender to render this 4096 by 4096 image. That's about 16 million pixels, and it had no problem rendering just that one single picture. You can imagine how long it would take if you had to render it using... Actually, no. if this was an animation, and you can, and I do have a few, and it is possible to animate these cars so that they skirt around the ground here. If I had an animation like that, if I were to make an animation and then render it, assuming I was still using the same settings as before, we're looking at about 2 seconds per frame, depending on what kind of frame rate I was using. The industry standard, depending on what you're looking at, is 24 FPS for film, 29.97 FPS for television in the US, 30 FPS for everything else, and 60 FPS if you want that 60 FPS experience. So basically we're looking at, what is it, like, because 4096 by 4096 is about 16 million, we're looking at rendering all 16 million of these pixels. You have to, basically what I'm saying is we have to render 16 million pixels up to 60 times per second. Of course, it's a little bit, of course, there are a lot of shortcuts, so actually there's, what I'm saying is, at most you're looking at 16 million times 60 individual pixels to calculate, but typically there are a couple of shortcuts so that you don't have to render that many pixels individually. But anyway, that's it. That's gonna be it for Blender. I'm gonna close this right now. Don't save. And now I'm going to start talking about the Sieve of Eratosthenes, because that's gonna be your first assignment. I may have a follow-up video sometime after this explaining more about what we'll be looking at, and in that I'm also going to include instructions on what to do, including a due date. But for now, let's look at the Sieve of Eratosthenes. A minute. So one quick Google search to find a grid of 100 numbers later, and I have this grid of numbers that we'll be using as our example. So, what is the Sieve of Eratosthenes? Well, the Sieve of Eratosthenes, to put it briefly, is a algorithm for looking for the prime numbers of. It's an algorithm to find the prime numbers up to a specific maximum number. So, you have this grid of 1 to 100 numbers, and I chose 100 because, well, actually there's no reason to choose 100. It could be any maximum number, really. But as our example, let's go up to 100. So, for reasons that will become apparent soon enough, we skip the number 1 and go to the number 2. Starting at the number 2, we start to look for all the numbers that are divisible by 2. That isn't the number 2. And we have to cross those out. So, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40. What I'll do is I'll just pause the recording so I can cross out all the numbers, and I'll restart the recording after that. Alright, I'm back. So, as I said, we were crossing out the multiples of 2. So after that, we go to the next number. So that's the number 3. Here we cross out all the multiples of 3. You can start to see an emergent pattern here, can you? Basically, the multiples of 2 are every number 2 up from 2. So starting at 2, If we go up 2 numbers, we get 4. 2 numbers after that is 6. 2 numbers after that is 8, 10, and so on. And those are all the numbers I crossed out. Now you could just eyeball this and use like basic divisibility rules to manually cross out all the numbers that are divisible by some number. Or we can just count, or here we can just count by 3s and just cross out all the multiples of 3 that way. So 3, 6. Actually, I'll just do this in a different color. 3, 6. Actually, no, that's a terrible color. 6, 9, 12, 15, 18, 21, 24, 27, 30, 33, 36, 39, 42, 45, 48, 51, 54, 57, 60, 63, 66, 69, 72, 75, 78, 81, 84, 87, 90, 93, 96, 99. Alright, and the number after that is the number 5. So let's color that in green. And if we go by, we can find all the multiples of 5. That's 10, 15, 20, 25, 30, 35, 40. Oh, I ended up skipping the number 4 because if we tried to cross out the multiples of 4, we would end up crossing out numbers that have already been crossed out. And that's simply because multiples of 4 are also multiples of 2. We would just be looking at every other multiple of 2. So 4, 8, 12, 16, 20, and those are numbers that we've already crossed out. We could just go back and cross them out again, but for the sake of example, let's just skip any number that we've already crossed out. 45, 50, 55, 60, 65, 70, 75, 80, 85, 90, 95, 100. For that same reason, we're gonna skip the number 6, because 6, numbers that are divisible by 6 are numbers that are both divisible by 3 and 2. So, numbers that are divisible by 6 are numbers that are divisible by 3 and 2, and those are numbers that we've already crossed out. So we can skip over to the number 7. Let's use a different color because, for the sake of visibility, 7. If we go up 7, we get the number 14. Cross that out, even though it's already crossed out. Continue. 21, 28, 35, 42, 49. 56, 70, 77, 84, 85, 86, 87, 88, 89, 90, 91, 98. Alright, the next number after that is 8, but we cross that out. We go to 9, but we crossed that out already. Number 10, that's already crossed out. We can continue to the number 11. We can cross out all the multiples of 11 here. 11, 22, 33, 44, 55, 66, 77, 88, 99. We can keep going with other numbers such as 13, but it turns out we ended up passing the point where we've crossed out all basically what I'm trying to say is we've actually long since passed the point where we've already found all the primes. So let's go back and see what all the prime numbers we ended up with are. So I'll go back with the red, and 1 is not prime, so I'll just cross that out. 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, 37, 41, 43, 47, 53, 59, 61, 67, 71, 73, 79, 83, 89, and 97. And that should be all the prime numbers between 1 and 100. Our first assignment will basically be writing a program that implements the Sieve of Eratosthenes. I'll later have basically an instruction sheet on what to do. I will say that you're basically free to use any programming language that you want to use, just as long as it's just basically just have the program working, and then we can use that program to make a parallel version of the sieve. So later on I'll have, as I said, I'll have instructions on what to do. And that's basically it for the first lecture video. I think I'll have a additional video. I might have an additional video, or at least the very next video will be further instructions on what to do, on how to program the sieve, and when it's going to be due. And that's going to be it for this first video lecture for CSE-5250 Section 2. Right, so that's it for this week, unless I have an additional video I need to put up. But that's gonna be it for the very first video. Right, thank you.